This is Boston University's Neurophotonics podcast. My name is Sung An, a second-year PhD candidate in Biomedical Engineering, and I am the producer and editor of the podcast. This episode, our studious hosts are joined by Dr. Emily Stephen as she discusses her journey from a computational neuroscientist to her position as a statistical neuroscientist at Boston University and a faculty statistician in the Neurophotonics Program. She also shares her contagious excitement for studying dynamic neural responses across multiple scales and how these scales affect each other. So, thank you for tuning in, and please enjoy the episode. Hello everyone, welcome to Neurophotonics Center podcast episode number 3. This podcast is created and produced by Neurophotonics trainees at Boston University. I am Sudan Duwari, third year Biomedical Engineering PhD candidate at Boston University. And today I'm here with my co-host.
I'm Dora Balog. I'm also a third year Biomedical Engineering PhD candidate. Today's guest is Dr. Emily Stephen. Emily is an assistant professor in statistical neuroscience. She works on statistical modeling and analysis of neural recordings across spatial scales. Her work involves constructing models that use strong prior knowledge about statistic anatomical features and state-dependent dynamical features such as coherence, neuromodulation, and active pathways in specific brain state to bridge spatial scales. So these models can explain apparent discrepancies in signals recorded at different scales and improve our understanding of the microscale dynamics that underlie macroscale biomarkers and pathological states. Hello, Emily. Welcome.
Hi. Thanks for the introduction.
Yeah, you're very welcome. It's great to have you here. So I gave a brief introduction about your current work, but to start off the episode, would you mind introducing yourself and just giving a brief history of your education and the research you have done previously that led you to the work that you do now?
Sure. Yeah. So Emily Stephen, I am an assistant professor in mathematics and statistics at BU. That's a bit of a shift for me. My training was not in math and statistics explicitly. It was kind of secondarily in math and statistics because all along I've been doing computational neuroscience. So I've always thought of myself as a computational neuroscientist. And in fact, my position at BU is as a statistical neuroscientist. Like they wanted someone in the math and statistics department who did statistical neuroscience, and that's why they hired me. So yeah, a little bit about my background. I started out, so I went to Brown for undergraduate. I did computational neuroscience there. That was a shift from electrical engineering, which is what I thought I wanted to do when I joined. But I fell in love with computer science and neuroscience and cognitive science and was not as excited about the engineering classes. So it turned out that they had a major for computation or a concentration for computational neuroscience, which allowed me to take computer science and statistics and math and neuroscience. And I was like, why not just do one major that does everything? So I did that, but I wasn't actually imagining that I would go on to grad school or do a career in computational neuroscience at that point. And in fact, I did some research in my senior year with a lab there. And let's see. As an undergrad, I did a summer program for sleep research with Mary Kerskadden, who's at Brown. And then later I did a thesis with Mike Paradiso, who does vision research at Brown, and really enjoyed it. But in my senior year, one of the graduate students in the lab where I was doing my thesis left to go into finance. It was kind of like, I'm going to go make money, guys. See you around. And then the same year, my brother, who was doing a PhD in operations research, kind of had the same thing. He was doing the PhD. He dropped out. He's like, I'm going to go into insurance, make some money. Bye, guys. And, as far as I know, they're both doing very well now. And so in my senior year, as I was deciding what I wanted to do after undergrad, it was like, oh, wait a second, maybe, grad school is not the perfect option. And so I went to a career counselor and got the advice, which I think is fantastic advice. You don't have to go to grad school right away. So if there are any undergrads watching, you don't have to go to grad school right away. I did consulting for a couple years after undergrad. So it was a company that does sales and marketing consulting for pharmaceuticals. I think nowadays they would call it data science, but at the time they called it operations research. And so I was doing basically solving optimization problems for sales forces, and so there are a lot of actually really like mathematically interesting problems there. And the people were great. And I really, enjoyed the day-to-day of the job. But in the end, I was always thinking like, oh, I'm pulling long hours. It's pretty stressful. And I'm just making a sales force more efficient. And like they're being better at bothering doctors. And like that didn't, sales forces are important. And I'm sure I would have come around. But it just didn't feel like the big picture of the job was like as satisfying as I wanted it to be. So I ended up deciding to come back to grad school. And I think that actually having that and knowing that, oh, I actually do like industry. I know I can do it. There are good people there. It has kind of complementary problems to academia, and just knowing what it is I'm choosing between made it a lot easier to get through grad school, because I think everyone has those times where they're like, why am I making like $40,000 when I could be making like six figures? And yeah, so I came to grad school. I have stories about that too. My grad school was at BU here in the graduate program for neuroscience. And so that's also computational neuroscience. My main advisor was Frank Gunther. So that's how I got into speech research, which I've done a fair amount of. But even then, I was leaning towards the computational methods side of things. So I worked a lot with Ori Eden and Mark Kramer, who are here, on developing new methods for basically learning from dynamics in speech tasks. And this was with electrocorticography data, so data that's on the surface of cortex after the skull has been removed in humans. Okay, so loved the PhD, had a pretty good time. Of course, there are, downsides. I can talk about that too if we want to get into that. So after that, it took me about 6 years. I went and did a postdoc with Emory Brown at MIT and Patrick Purdon, who's at MGH. So it was like a joint postdoc. And that's how I got into anesthesia research, which now I still do a lot of anesthesia stuff, and learned a lot more about statistical signal processing at the same time, which is largely what I'm doing now. And then, so that was a 4-year postdoc. I did another postdoc at UCSF, where we did some other new types of statistical models. By that point, I was like, I am a statistical neuroscientist. And very short into that postdoc, before I'd even been there for a year, I applied for faculty positions and was given the offer at BU. And it's my kind of dream place to be a faculty. And I knew it was going to be my dream place to be faculty. So basically, I accepted the offer, deferred for a year so I could finish up that postdoc that I had just started, and came back to BU. And, the rest is history, I guess.
What aspects of being a professor do you like best? Do you like teaching? Do you like the research? Is it both?
Yeah, so like teaching versus research, I think they go really well together, because teaching has a really nice structure to it. It's got very well-defined deadlines. You have to prepare for lecture. You have to make sure you're grading the homeworks and blah, blah, blah. And so it can kind of give you a structure to the day. Whereas if you're only doing research, sometimes it's hard to find that structure. Some of my happiest times were when I was a postdoc and I could, just do science all the time and just research. But it is kind of hard to find that kind of structure. And I think so they go very well together largely for that reason. But yeah, I love the teaching side. I love, I guess, advising probably even more than I love just like the teaching. Like I love it when we're a team working on this together and everyone has a certain aspect of ownership and we're all trying to kind of work together towards a common goal, versus like teaching sometimes feels a little bit more one-sided. It's like, I have something to teach you and I'm trying to convince you to learn it. And, some students think of it as take more agency than others. And it's like trying to inspire that, which is, I think, harder. It's just like can be hard. I teach introductory statistics for undergrad, and like some of the students who are there are very excited about it, and some of them are like, I just have to take this for my hub credit. But even that's like, actually, we've been putting a lot of effort into trying to make it like engaging and exciting, even for the students who are there. But I think if that were my only job, it would be kind of exhausting. Yeah. And then so, from the research perspective, it's definitely been an adjustment going from being the person who does, the coding and the data analysis and the figure generation to being the person who mentors the people who are doing that and then also decides what the future projects are going to be. And I love both of those. I love the mentorship side. I love just like being able to be creative and come up with projects that I think should work, that are pretty close to things that already work, and just like pushing things in new directions is really fun. But it is a lot more like writing, which is hard, and a lot less coding, which is easy and fun. So I have to remind myself that writing isn't what I'm doing. What I'm doing is coming up with cool ideas and convincing people that they're cool. And it's just the writing is just the medium for that. But if I could do it just by sitting with someone in a room and doing it, I would like it a lot better. But yeah, so I mean, so far, loving the job. I think there haven't been any major surprises. I think, even as a grad student, there was a lot of discussion about like what makes it really hard to be in an academic career. And so I was already kind of prepared for those things coming in and had already experienced them as a grad student and a postdoc. So I think that was kind of baked in. And so I've been able to just really enjoy the parts of it that are awesome.
Thank you very much for that introduction. We are all biomedical engineers, and we also have quite similar story to yours, like trying to do physics, math, chemistry, science, neuroscience, everything at once. And at least for me, and probably for you as well, biomedical engineering was the major that allowed us to combine engineering and science, math and biology, neuroscience.
Yes.
We do everything, which is why we chose that. So I think we're going to have a lot of fun discussions on science from that.
Yeah, it's basically the same thing. And if I'd only come up with biomedical engineering instead of electrical engineering, maybe. I mean, it's pretty fun to be in such an interdisciplinary field, right? Because I mean, especially in computational neuroscience, I think there's less of a historical bias about what you should be an expert in, right? There are people who do computational neuroscience who are engineers and who are mathematicians and who are, all these different things. And each one has a different perspective. And my perspective has kind of been like, instead of one field that I came out of, I kind of learned a little bit of a lot of them and constructed a very deep knowledge of computational neuroscience without any deep I mean, it has gotten deeper over the years, but it's like, I've been able to kind of develop expertise and interests really broadly without feeling like I'm constrained to any one like named field, which has been really freeing. And I think it was important to me all along.
Yeah, absolutely. For me as well, I started out with mice and gerbil models for speech. It was classic cocktail party problem solving. And then I was like, I want to do more on the human side, but I don't want to lose the computational engineering side. Can I find something like that? So BU, I knew it was interdisciplinary, applied to that program. Now working with Kamal for speech and cocktail party problem, and then FNIR. So it allows combining everything. And then wonderful example of interdisciplinary research, Neurophotonics Center, which the podcast is about. So I would want to ask you, how did you come in contact with Neurophotonics Center at BU? And how did you get into the role that you're doing right now? And how has it evolved from the first time you joined to up till now?
Yeah. Well, first, let me say, like, one of the things that I love about BU, and one of the reasons why it was the dream job for me, was that I knew from grad school how collaborative it is. Yeah. So both, graduate students can have co-advisors very easily. Different faculty are really willing to work with each other. And as someone who's, I'm a statistician, I have to work with data, but I don't generate data. It's incredibly important to me to be able to collaborate with experimentalists. And so when I came in, I knew a few people, but I actually, when I started faculty, didn't know a lot of people in engineering or neurophotonics. And so a part of this, so one person that I met in neurophotonics early on was Anna DeVore, because some of the work that she's been doing is very close to what I'm trying to do in bridging spatial scales and understanding, how the signals differ, if you're really just looking at one neuron versus if you're recording way up top. and we can talk about that. But I think just through Anna DeVore, my name kind of got in the mix for things. And I ended up meeting David Boas. And so I think the main reason I really got involved was there was the Neurophotonics T32 training grant. And as a part of that, they were really emphasizing data science and statistics. And they wanted to bring in a faculty member to be the faculty statistician, like an official titled role within the training grant. And they reached out to me and I said, that sounds like exactly the kind of thing I want to do. That sounds fantastic. So that's what I am. I am the Neurophotonics Training Program's faculty statistician. And so basically my number one role in that is to kind of support any neurophotonics trainee, whether they're funded by the program or not, like supporting them in their statistics and data science. So anyone who has, a statistical problem related to their research can reach out to me. I can, give little consultation sessions. If it's just an hour, that's great. If it turns into something bigger, if it turns into a collaboration, that's great too. But so that's I think the kind of ongoing role that I play. And then we have a few events that I'm also involved in helping to organize. So first of all, for the events, we have also a student committee. So Laura Carlton and Brad Rauscher are helping me organize all of this that I'm about to talk about. So I don't want to make it seem like it's just me. So the first one that existed before the training program is the Neurotech Talks seminar series. And so before the emphasis on data science and statistics, the Neurotech Talks were largely about, I think, although it was before I joined, were largely about experimental methods and like neurophotonics, right? Like how you do the data collection and things like that. And what we've started to do is to mix in more statistics and data science topics. And so it can still be led by a student, or we can bring in an outside speaker, and just trying to once a month have an opportunity for students to learn about some technology, whether it is experimental or whether it is data analysis and statistics. So the last one of those was yesterday. We had Katya from SCC come in and talk about the using GitHub, which is a skill that lots of people need and not everyone can learn in class. So we have found that there's been very good responses to that. Right, so those happen once a month. Watch out for your emails for that. Then twice a year, we have a quantitative skills workshop where we bring in and invite an external speaker to visit for half a week. So when they're here, they do like a large scale tutorial workshop for trainees that lasts for half a day. And that's open to graduate students and postdocs and all different types of trainees, regardless of their department. They don't have to be affiliated with neurophotonics. And that's twice a year. One other thing I want to mention for the students who are interested in maybe doing the Neurophotonics program is we have every year a data analysis boot camp. So there are 2 boot camps associated with neurophotonics. The first one is for the experimental side, and that happens in the first year. In their second year, students are welcome to come to the data analysis boot camp where it's supposed to be skills that are often not taught in courses that are really useful for statistics and data science. So this is things like research coding, best practices, GitHub, things like that. And then we've also set it up so that you can, at the same time, refactor your own code base and make it better. So hopefully it's not just like we're lecturing at you, but you're using the time to improve your own stuff. So that's all the things I wanted to say about neurophotonics.
Yeah, Sudan and I both participated both in the experimental bootcamp and then last summer in the data science bootcamp as well. And at least I have tremendously enjoyed it because, as you said, we never learn about Git and like how to use version control in classes. So it was really nice to practice there, and also gave us an opportunity to connect with other trainees at the Neurophotonics Center, people who are in different buildings, different labs, who we would not interact on a daily basis. So that was really nice.
Yeah, well, and the other thing, so there are 2 boot camps, but we have them at the same time and we share the meals. So we're trying to get the students all into the same place so that there's at least an opportunity to see people, to meet them across years in addition to within your year.
Yeah, absolutely. When we joined, there was only experimental side to it. We just hopped on to one building and the Met campus, and here just looking at different microscopes and imaging techniques and everything. But there was something missing. What about the techniques? What about the data science? What about the stats? And then second year, we got to do that. So thank you very much for organizing that.
Yeah. So to wrap up this section about the Neurophotonics Center, do you have any favorite things about the center that maybe students can utilize, or anything for the staff members? Like, what is your favorite thing happening at the center?
What's my favorite thing happening at the center? I mean, so far it's been the quantitative skills workshops. I feel like those are just such a great opportunity to get to know a researcher more than just going to a talk. Yeah, I don't know. I think that's so far my favorite thing. But the other thing to say is and from a student's perspective, the Neurophotonics Center has a really, really excellent tight-knit student community, and there's student leadership as well. So yeah, there's, you've got the podcast, you've got the neuroethics seminar, you've got the neurotech talks. And I think we're really trying to support that and to actually make to give the students as much agency as they want. And there's going to be a new, I forget what they're calling it, but it's a seminar series on brain-machine interfaces. So, I mean, and this is all just student-driven, student-led. So it's amazing how passionate and energetic the students are, and how involved they are in getting it going. So, as someone in a minor role of leadership, I'm just trying to get out of the way and say hey, here, we can give you funding, make it happen. So that's been really, really cool.
Yeah, that was wonderful introduction and talk about Neurophotonics Center. Now we're trying to jump into what you do, what kind of research you're doing at BU right now. Feel free to use slides if you have.
Sure.
And yeah, we'll start with what kind of research you're doing, and then we'll go into methods and everything.
All right. So, and interrupt me if I get to what's the word? If I get on my train, because it's I'm so used to doing this in a talk context.
Yeah, no, absolutely. Music to our ears. So you can keep going.
Cool. Great. Yes. So, broadly, I'm using statistics to understand dynamic brain signals. I teach a course called Time Series Analysis and Neuroscience Research that I encourage everyone to take. And so it's, time series analysis from a statistical perspective. And kind of the way I think about it is, I largely have a bias towards electrophysiology. So we're going to see this here, but not everything that I do is electrophysiology. But so we have recordings across all of these different scales, right? So maybe you have an extracellular single neuron recording. Maybe you have a much wider out extracellular recording where you can't resolve single units. Maybe you have, an electrode on the surface of cortex. So at this level, maybe you're recording from one neuron. At this level, you might be recording from hundreds of thousands of neurons simultaneously. And so, of course, we think about how neurons are interacting in networks and populations, and trying to understand kind of on a deeper level, or trying to get as much information as possible about what's happening at these scales when you're looking at a higher scale is kind of my obsession. Okay. So first of all, we have some challenges. The scales of recording don't always match the scales of computation. And so we're often imagining that, it's networks of neurons that are doing things, but if you're recording from one neuron, you only see a part of it. Or even if you're recording from lots of neurons, you're probably not recording from the whole network, although that's starting to change, and that's getting very exciting. And then there are principles of computation at different scales as well, right? So there's going to be certain operations that happen in the dendrites versus certain operations that happen at the level of a cell versus at the level of a population of cells, and so on. So the proposed scales of neural computation are all over the place. The proposed scales of recording are all over the place. And I think statistics is a really good tool for connecting them. And then the other one that I have is that you can have changes at the level of synapses that lead to changes at higher scales. And so a lot of neuroscience research in humans happens at the highest scale, where maybe you have EEG and they're very robust biomarkers. We know when people close their eyes, there's a rhythm over occipital cortex. We know that when people fall asleep, for example, you get this slow wave. And there are kind of models for how that relates to the synapse level and the network level. But there's often a big gap in understanding between the models, which operate at a very small scale, and the kind of clinically relevant biomarkers that happen at the largest scales. So again, obsession with kind of connecting those two things and connecting them in a really detailed way.
Sorry for the tangent, but have you talked to Dr. Matthias Stengel at BU yet?
Yeah, we've just started thinking about collaborating.
Yeah, and that's so exciting because Kamal sent me and Sung and Matthias, we all were like talking about we should all combine everything, FNIRS, EEG, deep electrodes, statistical analysis. Let's combine everything and look at it from, in naturalistic settings. They're already doing the walking, they're already thinking of doing the walking studies with ECOG or like deep electrode EEG. David Boas and the group, we're thinking about doing FNIRS and EEG outside. So if we combine everything, then probably we can like start.
And just think of all the exciting statistical problems that'll come up when you try to put all those things together. It's crazy. That's good. Yes, I'm very excited about that. Yes. And in fact, so I'm in the very early stages of starting to think about collaborating.
We were talking with Dr. David Boas as well, and then it came up, I think we should talk to a statistician about the kind of analysis we were doing and how to, correctly do our research. Mm-hmm. So your name came up. So that's
great. Yeah, no, I mean, I and if you haven't, it can be me. There are lots of people, but yes.
We know you, so
yes, that's what I'm going for.
I don't know if you talked to Dr. Kamal Sen yet. I think you would enjoy the talk.
I mean, I know him, I've met him, but I haven't talked to him directly about collaborating, but it's always easier when there's a student to bridge the gap. Right. Okay. So I've kind of broadly categorized what the questions that we're studying in the lab in two categories. One is like how microscale generators create macroscale effects. And largely I'm thinking about dynamics across frequencies and potentially interactions across frequencies. And then how do the dynamics vary across time, space, and brain states? So things like neuromodulation and things like that. And then just, my kind of list of things. I do a lot of exploratory data analysis in addition to dynamical modeling. And my best expertise is with electrophysiology, but I've started working with fMRI and optical imaging as well. And I'm very open to the idea of expanding beyond even those. So I've got a couple of examples, and I have way too many slides, but I thought I could at least start with this one, which is a little bit shorter, and then this one could get very long, and we can decide how deeply we want to get into that one. So just in terms of just characterizing dynamic responses and how they might vary across time and space and brain state, my interest in it started when I was in my postdoc at UCSF with Eddie Chang, where I was studying speech perception in ECOG. We've already talked a little bit about ECOG. So the electrodes are on the surface of cortex. This is in patients who have intractable epilepsy. And so they need to monitor their brain responses in order to figure out where their seizures are coming from. And so while they're being monitored for epilepsy, it's also really important to know which parts of the brain are important for speech and language, because you don't want to damage those when you treat them for their seizures. So studying speech and language in these patients is a very natural thing to do because it lines up with the clinical needs. So we were interested in studying responses to different acoustic speech features. And in particular, there are very fine-grained features, like, whether you're saying a fricative or a vowel or something like that. And then there are kind of features that we think have more to do with timing. So when the sound starts is a really important event. And there are events that are related to either syllabic or word timing, and we call those peak rate events. And so I had developed some pretty simple linear models for how to characterize the responses on an electrode. So here at the bottom in E and F, I'm showing responses on each electrode of many to either a sentence onset event or a peak rate event. And what we were doing I'm not going to go into a ton of detail about this particular figure, but the idea was that these responses look very similar across electrodes, and we can even think of them as being shared across electrodes. So this is almost like the response to a sentence onset event is a distributed neural response that has a much larger spatial scale than the response to an individual feature like a fricative or a vowel. And it was true both for sentence onsets and for peak rates, these kind of word or syllable level events. Okay, so from a statistical perspective, this problem shares a lot of similarities with other problems in neuroscience. And so I've been, since joining BU, starting to apply it in different contexts. One of them is in fMRI, where responses to an event in fMRI now are called hemodynamic responses. This is how the blood oxygen level varies as a function of time to a given stimulus. And so I've been working with Ariel Moore, who's working with me on a basically similar approach to try to understand how hemodynamic responses to speech perception, again, might vary as a function of space or even, different task parameters. So that's one application. And then another one, so Ariel is a neurophotonics trainee. I've got another collaboration with a few labs in neurophotonics, and Dora was also involved in this. I put these are the co-first authors for this paper that are up here. So this is a collaboration primarily with Anna DeVore's lab, where we're trying to study hemodynamic responses, but in mice. So now it's neurovascular coupling in optical imaging, how those vary as a function of space and as a function of neuromodulation. So we can look at acetylcholine and, in this case, it was norepinephrine, and characterize how the hemodynamics might vary when the animal is in a different neuromodulatory state, right? When their norepinephrine levels broadly are high or low. And so this is just the first step in a longer ongoing collaboration that I'm really excited about. And we're interested in looking at different neuromodulators and looking at potentially different types of brain signals, like how this is going to affect the electrophysiology in addition to calcium. And so that is hopefully, I'm really excited about that being quite a big research direction. And there's a lot of really interesting statistics in terms of how you can improve estimation of these and get really interpretable, basically neurovascular responses. I think one of the key questions here, and right now I don't think the statistical tools are answering it for us. The key question is, does the neurovascular response to neural activity, right? So when the brain activity causes the vasculature to increase its oxygenation, right? Does that response itself change with norepinephrine? Okay, so what we had in this paper is there's kind of two responses. There's a response to norepinephrine and there's a response to brain activity. And we tried to find an interaction. So the interaction would be the response to calcium changes depending on the norepinephrine level. And that interaction, our data didn't support, right? We didn't have the statistical power to detect that. That doesn't mean it's not there. It just means we didn't have the statistical power to detect it. And so I think what I'm really excited about is using statistical models that have better power to detect it and actually kind of borrowing the fact that there's so much similarity across, in this case, pixels, because these are optical recordings, to use that similarity across pixels to boost the statistical power and really try to find that interaction effect and test whether it's there. So very excited about that. And then, so that's it. All I had to say about the blue box, the blue question about dynamic neural responses. And then kind of I think of it as kind of the passion project side of the lab that I'm still kind of working to get off the ground is this idea of building models that can connect microscale biophysics to meso and macro scale cross-frequency effects. And some of this is easy and already done, and some of it's actually still an open question whether it'll even be possible. So this gets back to the point that I made on one of the earlier slides, which is how can changes at the level of synapses lead to changes at the level of the scalp? And so here's just a simple example of slow waves where, if you have, I think this is cats who are anesthetized, okay? And so in the anesthetized cat, if you have just at the level of a single neuron, it's firing in these on and off states. So on, the neuron fires, off, it doesn't. And that's at the level of a single neuron. On an electrode on the scalp, super far away, measuring from millions of neurons, you still see this kind of slow wave, right? And then all you have to do is increase synaptic excitation and it all goes away, right? So you have these very small scale changes that lead to these really large scale changes in dynamics. So this happens in humans too. So we have some human data, and I'm going to show this later. Okay, so in humans, you can look at, in this case, this is ECOG again, so it's on the level of cortex. You can see slow waves, so a continuous signal. If you just do an average of it based on the trough, so that would be like these troughs in the EEG. If you do an average, these are 3 different patients of the LFP, you can see that there's you have slow waves. And in fact, the single unit spiking, which they happen to have, this is not my work, they happen to have in these patients, happens at a very particular, here, maybe I can use my mouse, at a very particular time, right? It happens right on either the upswing or the peak of the slow wave. So this is kind of different scales again. So this is maybe tens to hundreds of thousands of neurons. This is 1 neuron. You can get even higher if you look at the spectrogram. So here, this is how the activity varies as a function of frequency. So if it's red, it means that there's a lot of power at 30 times per second. And if it's blue, there's not as much power. And the high, this like broadband power, which is broadband in the sense that it spans a lot of frequencies, it goes up when the spiking goes up. And so this shows up in the LFP, and actually it shows up at much higher scales as well. So this is kind of a way in to connecting these large scale signals to the microscale signals. And so I saw these results, sometime around, I guess it would have been grad school. And this is some work we've just kind of gotten out recently where we're trying to build models, statistical models that describe how that connection could take place. And I'm not going to go into the details on this, but the idea is we have just a very simple model of a patch of cortex. And in this case, we're only assuming that the contributors are synaptic activity. So you have excitatory and inhibitory synapses, and they have different impacts on the electrode, which is, recording from hundreds of thousands of them. You can include other generators here. You could include action potentials, calcium spikes, anything like that. And we're using these types of models to try to connect these biophysical parameters, how much are the excitatory synapses firing and what are their dynamics, into macro scale power spectra. And so we can build even theoretical power spectra that relate to a model that has a certain pattern of generators.
One quick question. When you earlier said that you were increasing the excitability of some of the neurons, was that like on the experimental level, like physically, with some drugs, or was it on the computational?
Yeah. So in this particular case, again, this is not my work. It was, I think it was a separate drug that they gave that basically counteracted the effect of anesthesia. But of course, you can do that in computational models as well. And I don't have any slides here on detailed biophysical models, and that's kind of disappointing because I've been getting really excited about them recently and actually so trying to connect. So here, from the perspective of someone who does theoretical neuroscience, this is an insanely simple model. It's linear, it's just based on filtering. And really, our claim is that in some situations, this is a good approximation to the very detailed nonlinear true network, right? Like neurons are not linear. And so we're working on validating it in several different ways. So validating it with data, validating it with more detailed theoretical models. And we're not expecting it to fit in every situation, right? And so we're like, how do we need to adjust this model? And when do we need to adjust this model to account for all the real nonlinearities that are in the system? And for that, I've started working, including with Dora, on using detailed biophysical models to bridge scales and to see if we can relate the models that might be impractical to fit to data and have a simpler model that you can fit to data that can bridge the gap between those. And I think in particular, one of the things that I think will become really important, and I'm trying to convince people is really important, is that rhythms and non-rhythms, or aperiodic activity or broadband activity, they're not two different things. They come from the same place, right? So what we're arguing here is that let's say if the dominant thing you're recording is synaptic activity, then the rate of the synaptic activity can be rhythmic, but its impact on the system will also have a broadband component. And so we're looking at ways that the rhythms and the broadband components in the mesoscale signals will interact as a function of the biophysical generators. So that's work that we've done kind of just in forward models. Now we're working on building up the statistics to learn from data about it. So interactions between rhythms, and claiming that they're really important and really structured, actually. They're more structured than people assume they are. And then there's kind of another class of models that's related to that, which is state space oscillator models, which assume that there's basically a clock, like a noisy clock in the underlying system, and you can learn the phase and the amplitude, like how in this picture, how long the vector length is, and also where it is in the angular location. 4 different frequencies, right? So we can have a model where there are 2 different oscillations, and we can actually split it up into a slow and a fast oscillation using a pretty simple latent state model. So this, in fact, can learn interactions between rhythms very well. And I'm excited to apply this to the broadband case as well. And then, so this is for like a single recording, but of course, lots of times we're recording from lots of either electrodes or channels at the same time. And so we've been building up models of how different oscillators can interact and how that might influence the patterns that you actually observe in the data. So this is some work from Wanqi Sin, who was working with me and actually defended last year on, these statistical models of oscillators. And that's what I've got. So I do have a picture of my whole group, or it's not everyone, but we've got most of the group here, and just acknowledging some of my collaborators and stuff. But yeah, science.
That's awesome. Thank you. So to zoom out a little bit, looking at the big picture, what are you most excited about in the field of statistical neuroscience? Just like seeing what's coming in the coming years.
So I think, and this has been true for a long time, and I know people have been talking about it for a long time, but so there's historically been a big divide between people who study single units and action potentials and people who study humans, right? Or like, fMRI, EEG, these large scale signals. And what's amazing nowadays is like we're starting to get these recording modalities that get the middle or get different levels of the middle. And so I think the really exciting thing is we're going to finally try to map so many of these really important effects that are known to be consistent in human recordings. Like human fMRI functional connectivity is super replicable, but it's still really controversial what's causing the functional connectivity, right? And that's true in EEG, right? It's super common if you do EEG research and you talk to someone who does ECOG or LFP research, they'll be like, oh, I never saw that, right? So there's a rhythm called the mu rhythm in EEG, which is like over motor cortex. And it's pretty robust in human EEG. It's like a rhythm that makes this mu shape when you're imagining moving. And I, talked to someone who studied ECOG, and they were like, oh yeah, that just doesn't exist in ECOG. And it's like, how could something exist at the big scale if it doesn't exist at the small scale? Like, there must be something at the small scale that's leading to this big effect. And it's just like, historically, it's been easier to study one scale, right? And finally, we're getting both the experimental data and the statistical and data science tools to actually try to link these things, which is just so exciting to me. It's like, I don't know, I think that's the thing that caught me, is just being like really unsatisfying in a way that it feels like it should be solvable, and I haven't been able to put it down.
Okay, so we're going to transition into a rapid questions and answers Q&A section to conclude this wonderful interview. So if you can just give us maybe one sentence as one even word.
Or try
some of these questions. You don't have to, but yeah. So to kick it off, do you have any habits or practices that help you stay creative and motivated in your research?
Oh, yeah, that's going to be a hard one. Yes, lots. One that I love is just going to a talk. I think even if it has nothing to do with my research, going to a talk is really energizing and reminds me why I'm here and how excited I am about neuroscience. So let's use that.
Yeah. Yeah, this interview is doing that for me. Yeah.
Okay, so outside of research, are there other interests that help you be creative or whatever you do that, keeps you motivated?
Yeah, definitely. So I try to keep physically active. I work out regularly. I get outside regularly. I think that's incredibly important. I've talked to people too. I think I had a conversation with Nancy Capel where she said something similar, which is like when her research is going poorly, she likes to do things that feel productive. So I think she got into like welding in grad school. And I got into figure skating in grad school. I'm like, as a, adult, never got good at it, but like I was getting better. And just the feeling of getting better at something when sometimes your research feels like it's hit a wall is really critical.
And that's why I'm crocheting right now.
Yeah, right. So actually I've got knitting that I pick up every once in a while. I've got, everything that I do, it's like I'm trying to find ways to feel like it's making progress because sometimes you feel that at work and sometimes you don't. And it's nice to have lots of ways.
Yeah, it's really nice to crochet a hat when your code is not working and you know that you can make a hat in one afternoon.
Mm-hmm.
Okay, so this is a little bit of a different question. If you could have a conversation with any neuroscientist from history, who would it be and why?
A neuroscientist from history.
Or you know what? It can be any researcher.
Oh man, that's tough. There's so many.
We knew this was going to be a hard question. So for this one, you don't have to say one word, or you don't have to be rapid fire. You can take some time.
Yeah, let me just process. I guess so. I'm not as into the history of science as I'd like to be. But I'd really like to have a conversation with like some of the originators of the like old school model neurons, like, the Hodgkins and the Huxley and like the Izhikevich and like the process of working out a mathematical model that was so useful and applied, can be applied so broadly. I think I'd really like to get their advice about what we should be doing today, Because there's just like that magic when the model is just complicated enough and not too complicated. And that's so hard to hit that sweet spot. So yeah, maybe like Hodgkin and Huxley.
That's an awesome answer.
Okay, next question. So neurotechnology is booming right now, right? Like in more so on the application side, for example, brain-computer interfaces and everything. So zooming out from the neurons or going to behavior or like brain-computer interface or any kind of neuroscience, everyday world application, is there anything that excites you the most?
About applications of neuroscience? Yeah, I mean, I think closed loop systems are really exciting. So, I think the tough thing with the really broad brain-computer interface stuff is that people want it to be non-invasive, and the signal's not great for non-invasive recordings currently. Could get better. And so, like, I'm almost more excited about things like closed-loop anesthesia delivery, closed-loop systems where, first of all, at least with anesthesia, it's still non-invasive, but like the effect sizes are really big. So you believe that it should work. As opposed to if I'm just like imagining something, it's going to be really hard to decode that without an electrode literally in my brain. And so I think, I guess that's one that I'm keeping track of that I'm pretty excited about.
I see. When you said closed loop anesthesia, do you mean recording like EEG, deep electrode or whatever, and then seeing certain brain dynamics being changed? Maybe consciousness, unconsciousness, pain and stuff, and then the machine titrates the anesthesia just precisely so that they don't. Is that?
That is exactly what I mean. Yes.
Yeah.
And it's actually really hard. So there are some serious side effects that can happen with anesthesia. People worry a lot about being awake during anesthesia. Yeah. That's extremely rare, but it does happen. I think a bigger problem is a lot of people have postoperative cognitive dysfunction. So they have delirium and stuff after surgeries. And one theory is that if you could give them less anesthesia while still keeping them unconscious, that they'll be less likely to have those side effects. And so having a really good way of telling based on an individual, because people vary a lot in terms of how they respond to anesthesia, having a really good way of telling for that person how much do they really need could actually be really impactful.
Yeah, I agree. I also heard that doctors or anesthesiologists who provide anesthesia, they work long hours, more than 24 hours in some cases, and there are a lot of cases of them making errors. So with the monitoring system that we have, so closed loop system probably with some machine learning techniques could be pretty good.
Exactly. Yeah.
Yeah, it's always nice working towards tech that will just decrease human error and just contribute to, the betterment of society. So to close out, one last question. So many of our listeners are early career researchers, PhD students, scientists. Do you have any advice for people who would like to pursue computational neuroscience or the field of neuroscience in general?
Probably depends on what career stage they're at. For undergrads, my advice is take a math course every semester, and math like engineering counts, computer science counts, math counts, statistics counts. So take a quantitative course every semester, just because even the specific course doesn't matter as much as getting used to thinking in quantitative terms and being able to read in quantitative things and thinking even algorithmically or in terms of systems. That's critical. For graduate students, I would say do whatever you need to do to stay passionate about your project and neuroscience more generally, and don't get too sucked in, right? So give yourself the space to not do work and have a really clear work-life separation, because I think you can... The challenge in grad school that I think is probably the hardest is you never really know if you're doing enough. And I think a lot of us really care about succeeding and about doing a good job, and we can go way too far in the direction of just burning ourselves out. And so taking a break, I encourage my students to take spring break off. That's one thing. But even just like taking a weekend and just not doing work can make a huge difference. So I think that's certainly my advice for graduate students. And I think it of course extends more broadly, but I think graduate students probably suffer the most.
Well, thank you so much for coming on the podcast and for giving this wonderful interview. Do we have any closing remarks?
No, I absolutely agree. I mean, whatever you said, especially for the graduate student advice, absolutely agree. We are doing that kind of stuff. Like we try to separate the work life from the regular life, and then trying to find some hobbies like running or crocheting or whatever, or cooking, where we get immediate satisfaction. So I think those advice, especially coming from you as faculty member and neuroscientist, I think that's going to stick.
Yeah, it means a lot. Thank you.
Thanks so much for having me. This was really fun.
Yeah, thank you very much.
Thank you for listening. If you liked this episode and want more like it, please take a moment to share it with anyone you think would enjoy it too. Next time, we will be joined by the co-presidents of our Neurophotonics Program's Neuroethics Committee here at Boston University as we discuss the work that the committee does to open up conversations about varieties of ethics challenges, the different ways neuroethics permeates our own research, and the implications of neuroethics throughout different stages of the research process. This episode was made possible by the support of Boston University's Neurophotonics Center and listeners like you. Thank you.